Hello everyone, and this is our lecture for 10.2. Let me see. Here we go. Okay everyone, this is our lecture for 10.2. And so first we have a definition of statistics. Now statistics can be used in two ways. It can be used as the name of an entire branch of mathematics involving gathering, studying, displaying, and analyzing data, or it can be used to refer to the actual data itself. So in 10.1, we talked about the gathering of the data and things to be careful of to make sure, questions aren't biased, the selection of the data itself isn't biased. And today, we're going to talk about displaying that data. We'll talk about that for actually a couple of lectures. All right, so first of all, we've got the difference between categorical and numerical data. Categorical data are data that represent characteristics of objects or individuals in groups or categories, such as black or white, inside, outside. For example, if we wanted to we're doing a statistical study about the color of cars that college students drove, then our answers would be things like red, black, white, gray, okay, as opposed to numerical data that are numbers, right? For example, in grade school, students may ask whether there's a difference in the distance that boys and girls can jump. The distance jumped is a numerical variable, and the collected data are numerical. So numerical numbers, categorical non-numbers. Okay, so the first part of this presentation is, of course, their slides where they go through and show these graphs and things, and there's not really a lot of room to do any interpretation. So I guess writing on, I should say. I'm not going to interpret them. But so what I decided to do is I just left the regular presentation, and we'll go through and look at each one and discuss the features of each different type of display. And then at the end, right, we'll have some questions where we completely go through the steps to create each type of display so you can see it actually being created and the thought process. All right, so the first one we're going to talk about is a pictograph. So that's simply put a picture graph, and it's used to represent tallies of categories. For example, categorical data might be seen in determining the month that the most automobiles were sold. The month is the category, and you use a symbol or an icon to represent the quantity of items. So right here, we've got recycled newspapers, okay, and each little bundle represents 10 kilograms of newspapers. So apparently this is a graph about the weights of newspapers, and it's called a pictograph, right, because we use little pictures to represent our counting symbol. Now something we've got to remember with all these graphs, right, all our graphs need titles, recycled newspapers, okay? They should have sources. I notice this one doesn't have a source, but if you're ever looking at an actual graph somewhere and it doesn't show you the source of where they got that data, it should be very suspect, okay? And it should have labels on both axes, okay? And if necessary, a legend or a key. This book likes to call these things legends, but they're more typically called keys to tell you what, in this case, each bundle of paper represents. So then you could be asked questions, well, how many kilograms of papers were recycled in August? 10, 20, 30, 40, 50 kilograms, right? In September, 10, 20, 30, 40, 50, 65-ish, right? Okay, so here they're going to talk about a different pictograph where you've got the number of students in each teacher's 5th grade class at Hillview. is depicted in a tabular representation in a table and then in a pictograph. So they gathered the data, and we're going to talk about this in a minute. This is a frequency distribution table, basically. And that's normally the first thing you create when you make your charts and graphs. Definitely the first thing you want to create when you're making a histogram that we'll talk about earlier. But they've also created one here where it's just a list of the teachers and then how many was in each class, and then they transcribe that into a pictograph. Notice we've got a title, we've got a key, right? Each little figure represents 5 students, okay, and we've got labels on the axes. Okay, again, no source here, but they may not have sources on any of these. Just keep that in mind if you're actually reading a graph. Okay, so a dot plot, also called a line plot, provides a quick and simple way of organizing numerical data. They're typically used when there's only one group of data with fewer than 50 values. So suppose the 30 students in Abel's class receive the following test scores. So here's their test scores. It's going to ask us to create a dot plot. So the first thing I need to know is what my smallest item and my largest item are. So look, we've got a 52 to 97, so 52 to 97. Okay, here's where they've created the dot plot. Okay, notice they made the scale go from 50 to 100. And then you just put an X above every score. So there's the 52. Okay, there must have been a 98 that we missed earlier, but I saw 3 97, so there's 3 X's there. Notice it's got a label, a title. Okay, and the number of X's above each score indicates how many times each score occurred. So I can tell that there is 86, 87, there was an 88, there were 2 72s, 175. Okay, now on dot plots, we have some different terminology. We can have outliers, okay? So an outlier is a data point that's significantly greater or less, like this one, than most of the others. Actually, when we get to the next section or the next, we'll calculate just how far that gap has to be considered, you know, for this point to be considered an outlier. Right now, we're just going to say, oh, one that's way far away from the others, or it could be, you know, very high. Okay, and then a gap is when you get a large space between points. My pen quit moving. A large space between points, like right here. Okay, and a cluster is a group of points that's located, you know, after or before a gap. Okay, this isn't a cluster because it's not separated from the other points. This is really most of the points right here, but then I've got a gap and a cluster. Okay, this is just what we just discussed. Oh, the mode, the data value that occurs most often. Let's go back and look at that and see if we can see the mode right there. So they didn't call it a mode on the display, but right here there were 4 82s, so we can tell that that's the mode. Okay, and we'll actually discuss modes in more detail in the next chapter even. Okay, so sometimes if we've already discussed the information and you know you're on the video, you can pause it if you want to read this stuff, but we've already gone over that. I'm just going to go on. Okay, then we have stem and leaf plots. Okay, a stem and leaf plot's similar to a dot plot, but the number line's usually vertical, and you use the actual digits rather than an X. So notice it has a title. They all have to have a title. Okay, this is another one along with the pictograph that must have a key or a legend to tell you how these numbers are read. For example, depending on what if this was a score, you know, these test scores were between 1 and 10, and this represents a decimal, and there was a 5.2, a 7.0, a 7.2. And it's odd here that they've used that one. Usually you take just the first score and your key, and you'd have 5/2 equals 52. right? But it must have a key. Okay, and so the way you read this again is, oh, there was a score of 52, that no one scored in a 60, someone made a 70, someone made a 72, another person made a 72, right? There were 397s, oh, sorry, 397s, a 98. Okay, a stem and leaf plot. Advantages of stem and leaf plots, they're easily created by hand and no actual data values are lost. Let's go back and look at that. Look, I can tell when we did like the frequency distribution table, and I do that a lot of times when we come in after we've taken a test and I put up, A, B, C, D, and we'll put, 4 people made a C. Well, we don't know if they were all 78s and 9s or all 70s and 71s. Right? But on this type of display, no actual data is lost. I can see that, oh, look, all those in the 90s were high 90s, okay? And in the 70s, they were spread out. So no data values are lost. But a disadvantage is when there's a lot of data, it becomes unmanageable. Think about putting up the test scores for every student in the college. Do you really want to create a stem and leaf for that where you have to display every single data point? Okay, so here's how to construct a stem and leaf. Once again, if you want to pause this and read the section, I think it's a 2-page, 2 pages, you can, but at the end, we're going to go over the specific steps and work through creating a stem and leaf step by step. Okay, we have something called back-to-back stem and leaf plots also, where you can compare 2 sets of related data. So in this case, Abel again is comparing test scores, but she's comparing her 2nd period class to her 5th period class. Okay, so notice again a key. Now we need a key for each one. Okay, so this means I'm reading this direction, 50, right? 52, someone made a 61, and then this one is read in this direction. Okay, so I can tell at a glance, oh, well, these students as overall made higher than these guys. They're, about the same number of 80s, more 70s and lower here, and higher grades here. Is there something different that was done in the 5th period class to help the understanding? That kind of thing for comparison purposes. Okay, now here's one of their examples. It says, group the presidents into 2 groups, George Washington to Rutherford B. Hayes and James Garfield to Ronald Reagan. All right, so I need, here's Rutherford Hayes. Let me actually get a pen here, guys. All right, so right through there. Okay, and then I think it's going to make us, ask us to make a back-to-back stem and leaf, but this is one of the ones where they've already created it, so we don't have to know too much. I'm going to have to erase that line, I believe, before I can go on. Okay, create a back-to-back stem and leaf plot of the 2 groups to see if there appears to be a difference in ages at death between the 2 groups. All right, so the first thing they had to do was figure out the bottom age and the top age, okay? And so make their stems go from the 40s to the 90s, and then they just went through and listed the age of each president from the last half and from the first half. Okay, then you can kind of compare, what did it say, which one seemed to live longer, okay? And so an argument could be made, oh, the later presidents seem to live longer. If I just look right here in the 90s, there were 3 in the 90s compared to just 1 here. But if we look overall at all of the data, right, let's say, and of course, lived longer, what do you consider to be lived, to be old when you died? But let's look in the 60s, since it's about the same amount, and probably 70s, 80s, and 90s where, would consider, oh, that's living longer than dying in the 40s and 50s. And so notice in the 40s and 50s, these later presidents, I had later presidents more dying in the 40s and 50s, about the same in the 60s. But well, the 80s and 90s together here are also about the same number, died in their 80s and 90s. A considerable number more of the early presidents lived into their 70s. So if you look at 70s, 80s, and 90s as being able to, as thought of as living longer, then it was the earlier presidents that lived longer. If you restricted it to simply the 90s, okay, that could have been a question. Then it would have been the later. But just looking all at which ones lived longer, probably the earlier ones, because also comparing, oh, well, look how many of the later ones died young. Okay, and that's just what we've already said, right? Okay, a frequency distribution table. So they're just calling them frequency tables. Okay, and this is what we were just talking about. You do not have to have both of these columns. You do have to have, now this should have a title, and notice it's still the ages of presidents at death. So they took that same information that we had in that chart right before they made that stem and leaf, except they're not doing earlier and later. They just said there were 2 presidents that died in their 40s, and 5 in their 50s, etc. So you can do either a tally, or you can just write the number. This label up here on top should always be frequency, right? Should always be frequency, even if you're using tallies to represent your frequency. And it should have a title. Okay, and then this should have, like this does, ages at death, some kind of title. Okay, these are called classes, right? Your classes, there's some specifics that we need to know about classes. For one thing, they've got to be the same size. There are exceptions that your first class and your last class can be larger. For example, when we were talking about making the frequency distribution table for grades, and I put up A, B, C, D, F. Well, think about what those numerals are. An A is 90 to 100. A B, 80 to 89. A C, 70 to 79. A D, 60 to 69. So all those are the same. But an A, not 90 to 99, 90 to 100. And an F, 0 to 59. So it is acceptable for the first and last class. I don't know that you'll see that in any of your problems, but the first and last classes may vary, but all the ones in the middle have to be the same size. The first number in your class size is called your lower class limit. The upper number is called your upper class limit. And you'll be asked, what's the class size? Now, it's very hard. Students look at this and say, oh, the class size. And remember to take it from a middle, not a first or last one, because it may be different. And it's easy for a student to say, oh, 50 to 59, the class size is 9, right? 59 minus 50. But these numbers go from 0 to 9. The class size is actually 10. So when you're finding your class size, don't subtract these 2 numbers in the same class. Subtract one above the other. 60 minus 50, 10. 79 minus 69, 10. 80 minus 70. So when you're determining class size, remember to subtract this way, not this way. Okay, let's see. Characteristics of frequency tables. So each class interval has the same size. We said that. The size can be computed. This is silly. Here's, I guess, another way you can do it. Subtract the horizontal ones that we were just talking about, don't do, and then add one. Okay, or you can do what we said and just subtract the vertical ones. Okay, we know how many data values occur, but we don't know the particular values themselves. So we lose a little bit of information, right? So I know that there were 10 presidents that made it to their 70s before they died, but I don't know, were they all like 78, 79? Were they early 70s? So we lose a little bit of information over what we could see if we had would have made a a stem and leaf. Okay, as the interval size increases, information is lost. Well, that happens on any interval, but of course, the bigger the interval size, the more information that's lost. Suppose you'd have made those 20-year intervals, then you'd really have lost information. Oh, wow, if you went from 60 to 80 for your interval, you wouldn't know how many died in their 60s or their 70s. Okay, and class intervals should not overlap. Okay, that's something I hadn't said yet. Yes, they cannot overlap. So you can't go from 50 to 60, 60 to 70, 70 to 80. You'd have to go 50 to 59, 60 to 69. Don't overlap those class intervals. Okay, histograms and bar graphs. A histogram is made up of adjoining rectangles or bars. The bars are all the same width. Okay, and the scale on the vertical axis must be uniform. This is important. A distinguishing feature between histograms and bar graphs is there's no ordering on a bar graph. Ordering is not necessary. Bar graphs are used with categorical data, like we were talking about earlier. If we want to do study the color car students drove, it wouldn't matter if we put the red bar first or the blue bar first. Right? Whereas histogram uses numerical data only, so it has to be ordered, right, in numerical order. And on a histogram, the bars must touch. That's what this means, adjoining up here. The bars must touch, and they got to be the same width. Okay. So here we're still doing the ages of presidents' deaths, so still all that information from that table. They've just made a histogram. And when you create a histogram, the first thing you're going to do is make a frequency distribution table. So let's look back for a minute at this table. Notice two presidents died in their 40s, 5 in their 50s, and then 12. Well, here's what we have here. In their 40s, 2 presidents. In their 50s, 5. In their 60s, it goes up to 12. Okay, we got to have a title. This is always frequency. Okay, and then here's another label. Okay, now here's a bar graph. Look at the difference between what a histogram looks like and a bar graph. Bars aren't touching. Histogram, the bars are touching. Okay, the order that we put these in down here, right? Tom, Dick, Mary, Joy, doesn't matter. The order that you align these does matter. You can't have the 40 to 49 over here and the 60 to 69 over here. You got to go in numerical order. Okay, here's a double bar graph. Here they've taken that information on the ages at president's death and used those stem and leaf from where we had the later presidents versus earlier presidents, and made a double bar graph, right? Green bars represent the ages of the later presidents' deaths. Okay, notice also it's possible, it's not always great, but it's possible sometimes in a histogram to just put the number here instead of the range. You can say, oh, 90s, 80s, 70s, 60s, 50s. Okay, also this one's sideways. Notice the frequency is here. A circle graph. So a circle graph, also called a pie chart, is used to represent categorical data. Again, right, categorical data. It consists of a circle that's partitioned into sections, and each section represents a part or percent of the whole. So a circle graph, this is what's important about a circle graph, shows how parts are related to the whole. All right, so construct a circle graph for the information in the table, which is based on survival and death rates of the crew and passengers of the various ticket classes on the Titanic. Okay, so the first thing you got to do when you're making a circle graph is you have to extend your chart of information to include the percent and then the degree that your sector needs to be. Okay, so they probably do that here. So the entire circle represents the total 710 people. Once again, I think these instructions here, I'm going to slide on through. You can pause it and read them if you want, but I'm going to go on to where they're actually creating it and explain this. Okay, so right here, notice they've extended their little chart they had. So first class, there were 710 total, 202 in first class, right? So they found that percent, 202 out of 710. 28.5% of the people on the ship was in first class. And then you want 28.5% of 360, because the entire circle is 360 degrees. 28.5% of means multiply. So I'm going to multiply 28.5% times 360. Remember, when you're using a percent, we got to change it to a decimal. So I'd have 0.285 times 360. Notice it says approximate degrees. If you add these up, 361 degrees, because they've rounded here. They've done approximate, and most times that's the best you can get. Okay, these numbers don't come out to be even percentages. All right, and then once you know the degree for each sector, right, you draw it. Okay, we're not going to go to the particularly now, you're not, but even if we were in class, we wouldn't go to the trouble to get out a protractor and measure our degrees. But if you're actually creating a circle graph for some statistical data, you would do that. But here we are going to figure out the degrees and say, oh, 25%, that's like a fourth of the pie, and we would get that, whatever that is, just right at 90 degrees. Okay, all right, so here's our actual examples we're going to work through. All right, let me get my pen back. 6th grade students reported the number of apps that they downloaded to their smartphones. Construct a dot plot from the given results. So the first thing I need to do is say, okay, my data goes from zeros, I've got a 25, okay, to 25. So if I'm making a dot plot, and this is really hard to draw on here, it's not too bad writing like with equations and things, but when I'm making these charts and graphs, because where I'm writing over here to the right, I can't see, it doesn't stay over here. It stays up on the board or on the screen, and I'm not writing there. All right, so we need to go from 0, and let's do like they did, 5, 10, and there's no set scale on what you're going to use on a dot plot, Okay, so here's 0. First of all, we're just going to make our number line. Okay, every chart and graph that we make, also, by the way, since you'll only be doing this online and won't physically be doing this semester, I'm sorry, guys, right? That one thing you won't have to worry about, because I think all these online is just a multiple choice, you pick it. But if we were actually constructing this, okay, don't forget we need a title. Okay. So, and you might keep up with your data like this, so 10, 11, 12, and you just put an X above every one. 5, 7, 3, 0, just to do it quickly. 7, 3, 0, 2, 0, 10. 2, 0, 10, 12, 9, 0, 0. 12, 9, 0, 0. And try real hard. You notice that my first row is going kind of wobbly there. Try to make it in a straight line, which is way easier to do on a piece of paper other than this tablet. 15, 17, 25. 15, 17, 25. 7, 8, 10, 12. 7, 8, 10, 12. 13, 0, 0. 13, 0, 0. 10, 14, 0. Okay, 10, 14, 0. And there we are, a dot plot. And then we can tell, oh, by far, the most sixth graders don't download any apps on their phones, right? We may have an outlier here, a data point that's far away from the others. I don't see any gaps or clusters in this particular display, but that's all there is to creating a dot plot. Okay. We got to erase this stuff or it just stays on to the next screen. So I'm going to get my eraser here. Okay. Okay, now we've got HKM employs 30 people of the following ages. So that draw a stem and leaf plot for the data. Okay, same thing. I need my highest and lowest data value. I see an 18, I see a 62, 63. Okay, teens to 60s. So if I'm drawing a stem and leaf plot, my stems will be teens, 20s, 30s, 40s, 50s, 60s. Okay, I need a label up here. Okay, and we should have HKM ages, a title for the overall graph. And then I just go through 58, 21, 63. Here's 58, 21, 63, right? Do the exact same thing. Once again, try really hard to keep these vertical components lined up. 48, 52, 24. 48, 52, 24. 52, 37, 23. 52, 37, 23. 23, 34, 45. 23, 34, 45. 46, 23, 26. 46, 23, 26. 21, 18, 41. 21, 18, 41. 27, 23, 45. 27, 23, 45. 1, 2, 3, 1, 2, 3, 4, 45. Trying to keep those lined up. 32, 63, 20. 32, 63, 20. 19, 21, 23. 19, 21, 23. 54, 62, 34. 54, 62, 34. I think that's a 2. Okay, and then make sure you have a key, right? Gotta have a key. So all I'm going to say is how to read that. Okay, because sometimes I could even have this key might be that, hey, this represents 181, 214, 233, 236. We're at 374, 324. Or like we said earlier, 1.8, 2.1. Or it might just represent 18. So you got to have that key. Okay, so that's a stem and leaf. And then once again, we can tell a lot of information, how many were in their 20s. There's about the same number in their 30s, 40s, and 50s. Only 2 in their teens. Okay, answer all kinds of questions about it. Now, if it says an ordered stem and leaf, you got to go back and put these in order. But in just a stem and leaf, if you're just creating a stem and leaf, they don't have to be in order. Your leaves do not have to be in order. Okay, 5 coins are tossed 64 times. A distribution for the number of heads obtained is shown in the following table. Draw a bar graph for the data. Notice this is a frequency distribution table. It's just horizontal instead of vertical. Okay, so if I'm drawing a bar graph, whoops, I need my pen. Okay, I gotta have a vertical and horizontal axis. This over here is always frequency on a bar graph or a histogram, right? The frequency. Got to have a label down here. We're just going to keep it simple. Coin tosses. Coin tosses. Okay, so it's number of heads. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. And because they asked me to draw a bar graph with this, technically those don't have to be in order, but when we have numerals, we do want them in order. Okay, and I need to go up to 20, so maybe 5, 10, since I've got limited space here. And how I knew that, I'm looking at my frequency, and my biggest number there is a 20. So 5, 10, 15, 20. Okay, 2, I'm going to make my bar go up about 2 on the 0 heads. 1 head had 10, so I need a bar that goes up that high. Okay, 20 for 2. 20 for 3 heads. 10 for 4 heads. And 2 for 5 heads. A bar graph, right? So this is always frequency. You need a label down here, and ideally it should have, a title up here. Seniors at Sierra High were asked about their preferred online social networking service. The following are the percentages of students in the top 5 responses, those with none of the top 5. What? The following are the percentages of students in the top 5 responses, okay, and those with none of the top 5 responses. So 1, 2, 3, 4, 5, and then a 9. Okay, construct a circle graph for the data. Getting my pen back. Okay, so the first thing I got to do, I need a calculator for this. So the first thing I got to do, and they've already given me this in percentages, but I'm going to add a column here for degrees. Okay, so 64%, I need to know how many degrees that would take up. So 0.64 times 360 is 230.4 degrees. So I'm going to say, well, that's 230 degrees. 0.22 times 360, 79.2 degrees. So rounding, I'll just say 79 degrees. 0.02, right, times 360 is 7.2 degrees, so 7 degrees. 0.01 times 360 is 3.6, so we're going to say 4 degrees here and 4 degrees there, and then 10% would be 36 degrees. Now I suggest you add these up. So what do we got? So 40, 51, 60, 130. Oh, we came up exactly 360. But you need to be close to 360. I mean, you might be 361, you might be 355, depending on, how the rounding went. We were lucky and came up exactly 360. But if you're 364, right, or 356, you might think, wait a minute, I should be off somewhere. So then you make yourself a circle, and we all know that I can't draw. Okay, and then so I need 230 degrees. Well, I know half of that's 180, and I know this is like 270. So I'm going to say something a little, if I went straight across here, that's 270, right? So I need 230 between 180 and 270. Let's see, maybe, whoops, like this, and then we label it. Okay, Facebook. Okay, 64%. 79 degrees, straight across here would be 90. So I'm going to go maybe, whoops, a little too far, like this, and do Twitter. 79%. Okay, so we've got 36 degrees here. I'm obviously off on my drawing here because I'm not going to fit in a 36 degree one here. And this is why we would ideally, we would use a protractor to know exactly where these degrees go. So what's this, 15 degrees and 36, 51, might not be as far off as I thought. So I'm going to do like this, say none, right, 10 degrees, no, 10%. Okay, and then I'm going to split this here and then split this. And when you can just, if you have something like that, you can do this, MySpace, Google, LinkedIn. Okay, then it also needs a title down here. So you would write Sierra High Senior Social Networking Preferences or something. Okay, looks like that was the last example I put up. I missed a histogram example. Okay, so if you have histogram questions, be sure, I should have had one in there, but apparently I didn't. So be sure and let me know if you have any questions. Okay, we're going to do some more talking about displaying data next time. And I look forward to actually talking to you guys. All right, bye.